Right. Well, all right, everybody. Welcome to those of you who were able to join. Quick mic check as always to make sure that you guys can hear. Thumbs up or even a verbal would be good.
Loud and clear.
Perfect. And then of course you can see the screen perfectly fine as well. It's safe to assume.
Yep.
Awesome, wonderful. I appreciate that. Thank you all. And we'll go on ahead and kick this off here. We got a recording going, so we don't have the same debacle as we had last week. Well, welcome everybody to week 4. Congratulations for sticking through it, making it this far, putting in that effort that I guess you guys have already kind of discovered requires no major changes in, excuse me, in the course or how it is presented. Excuse me one second. Ooh, tickle there. In that the battle rhythm is pretty simple. You guys have a quiz, you guys have homework, you got discussions, and you have your um, summaries to write. And that's basically it. So 4 things to do every week. I will say, whether you're here in attendance or whether you're going to watch this later on because you weren't able to join, or if you're going to rewatch it again because there was something you missed, I cannot count you guys as present for the week if you don't turn in at least one assignment of some type. Okay. Whether it's the summary discussion, or whether it's the discussion itself, whether it's doing a quiz or even the homework, you have to do at least one assignment for the entire week in order for me to count you as present. And so I say that because there's been a few, not very many. I think there's only 2 out of the 27 that I've had to count absent the last 3 weeks. And the assignments are getting turned in. They're getting turned in a little late, which is okay. However, I can't count you present if you don't turn it in within the week. So just kind of keep that in mind when you guys are doing your assignments. The vast majority of you, this isn't going to be an issue, but I wanted to kind of point that out. So with that, we will proceed. Again, guys, 2 weeks left in the class. Thank you for all the efforts. As always, reach out if you have questions, and we're going to continue our discussion tonight on semiconductors before we shift over to power supplies. Okay. So with that, optoelectrical devices is what we're going to kind of be discussing tonight. Opto, if you aren't familiar with it, basically means working with light. So you essentially have electrical devices that are using light in some capacity in order to conduct. Okay. So a lot you see in front of you on the screen. Essentially, what we have going on here, if you don't know, is that we can actually only see or perceive rather 4% of the light that's out there that actually exists. So of this entire spectrum of light that exists in some capacity, we can only see 4% of it, which is a fascinating conversation all in itself. As you guys may already know, there's light waves all around us. The vast majority you cannot see, and something that people don't really kind of grasp or gravitate towards is that light in itself is matter. Light is matter. Okay. So here you see your long wavelengths, and of course you got your short wavelengths. So essentially, these long wavelengths here on the far left side of the scale are your broadcast band and your radio and your radar. And as you move towards the right, you start getting into tighter groupings or shorter wavelengths. Okay. And so within the middle here, you can see the infrared and the visible light spectrums, the different spectrums that we know of, ultra from infrared all the way to ultraviolet. And of course, these are different nanometers, if you will, that they present themselves in. And so you have IR, which we technically cannot see, and then you start kind of creeping on over here to the visible light range, and then of course you can't see ultraviolet. That is a differing wavelength on its own. Um, but so overall, this is kind of the overview when it comes to light, and we're going to be kind of centering our discussion, if you will, in this area right around here. Okay. All right. So here's a picture of some what are what known as photocells. These are the oldest, and they're still in use, if you will, when it comes to photocells. They are sensitive to changes in light or internal resistance changes off the intensity. Okay, so basically, if you can remember, resistance equals intensity. The brighter the light this thing is putting off, the more it will conduct. The less light, the less it will conduct. A general rule of thumb. Okay. Um, So you can kind of see in some of these here, specifically this one, you can kind of see the optoelectrical coils. That's what this is known as. Uh, a lot less visible here, and of course, really, really tight over here. Okay. This is kind of a cartoon depiction of a photovoltaic cell. Right? So basically, you take a DC voltage or a solar cell, and of course, it produces some type of a charge. Okay, so this is tied into mains power nowadays, but they used to have to be stored directly into a DC battery arrays. So I essentially myself, I live off of, well, I don't live off of solely, but I have a 33 kilowatt system in my home because we have a lot of roofing. It's borderline a very small industrial type of system. And it produces about 58% of my power throughout the year. And essentially during the daytime, as light is hitting it, it's producing energy. So much so that that energy is actually feeding the main power grid. I can't store it, of course. So when the sun goes down or as soon as it stops producing to the capacity, I start using off the grid. Um, but essentially, when it comes to these type of things, these photovoltaic cells made up of P-type, N-type material is essentially how they work. And we're going to hone in a little bit on this P and N-type material because this is how our opto isolators are going to be using, similar to a normal diode when it comes to that. So just a quick plug, if you want to know more about photovoltaic cells or any type of light sensitive devices, feel free to dive deeper into it offline when you get a chance. There's lots of resources out there, including some of the ones that we've introduced you guys to. Okay. So here you see this is a p-n junction photodiode. Okay, it looks very similar to your standard p-n junction diode, except you have this little icon here that says light. Okay, this is actually designed to work in reverse bias mode. So what we're going to have here is we're going to have a negative potential on our anode. If you guys remember the reverse bias, we've been talking about this quite a bit. We'll have a negative potential on here, and we're going to have a positive potential on our cathode, which means we're sitting in reverse bias. Okay. It does control current, very similar to how a diode does. But once it gets into reverse bias mode or RB mode, let me go back one. I apologize. Got a little excited there. Once it's sitting in reverse bias mode as it is, it's waiting for something else. So that's something that it's waiting for is light. Okay. So that light will enter the depletion region. And if you guys remember, we've talked about this quite a bit. Here's our depletion region right here. Okay. So we're going to have light. It's going to be coming in some capacity. It's already right here. It's going to be entering this depletion region. And as I alluded to earlier on, the more light that gets in here, the more current is going to be allowed to flow. Okay. The more light that gets in here, the more current is going to flow. Now we're going to see what this looks like. Um, very soon, but this is the schematic symbol for your this opto this diode, this light emitting diode, this LED. Okay. And it's waiting here for light to come in. So as this light hits and it starts to conduct just as normal, guys, it's going to conduct in that direction. Okay. It's going to allow current to flow that way. Again, more light equals current will flow. And of course, the higher the resistance, of course, there's not going to be any light coming in, so it's going to have a pretty high resistance. Okay. Okay. Here's a p-n junction diode, with I being your intrinsic layer, which basically what this does is it extends the depletion region. So before our depletion region was pretty thin. And with this intrinsic layer, what we're doing is we're extending this depletion region. Okay. Again, though, it still needs light to come in as before to allow current to flow. Okay. So this is kind of a scoped in look in terms of what's going on there. So essentially what you have versus your normal p-n junction diode is you have an intrinsic layer. Okay. That's extending that depletion region. Okay? And of course, this is what a photodiode package might look like. Okay, so you have the lens on top here, which lets light in. Okay, so light's getting in here. It's showing kind of light making its way through there. The p-n junction diode is at the bottom of the case. All right, you have your anode, you have your cathode. Normally, I think I've said this to you guys before. The cathode is longer, has longer legs and pins, and sometimes has a notch on top. Okay, but this is our cathode. I'm assuming at the angle, this was a little bit longer. That's how they knew, or it may have a little notch here on the top, or it might have a little notch here on the bottom. That's how they know. Okay, so again, this is what that package might look like. All right, and there's that image that I told you about. So here's a voltage divider using a photodiode. Okay, voltage divider network using a photodiode. There's the symbol that I told you about. This is your diode, your photodiode. This is currently operating in reverse bias mode. Chris, how do you know? Because we have a positive potential on our sitting on our cathode, and we have the negative potential that's sitting over here on our anode. Okay, so it's sitting in reverse bias node. Okay. Again, all this is waiting for light to shine in. It might have a little minuscule current flow coming through here, but it's waiting for that positive potential uh, to be increased based off of that light that's going to hit the diode. Once the light shines in, that intrinsic region that we just discussed is going to kind of shrink down and current's going to flow. Okay. And it will occur once that current does start to flow, it's going to give us a voltage drop across R1. All right, so we're going to start to see a voltage drop across here. And whatever that voltage drop is going to be across here, it's going to be equal to the voltage out. Okay, so sometimes when you're looking at a circuit, you might have a resistor in here, and maybe you can't quite measure off this. Okay, assuming this is big enough for you to measure. This isn't packaged in. We've talked about that quite a few times. But it might have these things sticking out over here, also known as test points. Okay, so that means you could take your leads and put your leads across here, and the same voltage drop that you're getting over here on this side, we'll say it's 2 volts. You're going to measure 2 volts over here. Why? Because this is in parallel. That's the way the circuits are behaving. Very similar to what we used and looked at before. Okay. Okay. Here you see a darkness on. Here is a darkness on a DC switch. Okay, don't ask me why it's called that. That's just the name of it. But more importantly, this is a Darlington pair. Chris, how do you know? Because we have 2 transistors. We're going to start diving back into these transistors. I know we left them. I'm going to say this a few times tonight, but we're going to be scoping our way back to them. Whenever you see these transistors in this pair, just like this, okay, the where you have your emitter tied to the base of another one, okay? Just in this pair that you see here, this is known as a Darlington pair. Q1 and Q2 make up the Darlington pair. Okay, so the light's going to provide biasing for the base of Q1, as you can see here. All right. Once bias is created, it's going to allow current to flow. Here we have over here our friend. We have an SCR. We talked about this last week. Okay. Then we have our gate to the SCR. Of course, again, you guys kind of recall this is our gate to the SCR over here. Once current is allowed to flow through Q2 and Q1, it will be the trigger for the SCR. All right. Once that SCR is triggered, it will allow current to flow to our load. Okay, we'll get a nice current flow to the load. Even if we lose the light on for Q1, once it's triggered, that SCR will allow current to flow until there's no power. The SCR is shut off or the SCR goes in reverse bias. Guys, we talked about this a couple of lessons ago. Once this SCR is triggered, guess what? It's going to stay in that state until something forces it out. Okay. And that's basically what that's telling you. So once we have the correct current flow, or once these things once light is on here to turn on our Q2 to allow current to flow accordingly, and it triggers our gate, SCR will allow current to flow to the load, and it will, whatever this load is, it could be a motor, it could be a light, anything, it's going to allow it to do what it needs to do. Okay. Something that's pretty fascinating about this, and something that I hope you guys have noticed. I know it probably feels like we moved a little bit quickly through some of these concepts, but the reason why we have is to give you a very, very basic understanding of them. We're going to build them all together. And as you can see in some of these differing schematics that I'm starting to show you, while you may not remember the exact principle off the top of your head, I think by now you guys should recall that, hey, this is being used to control and it's waiting for something to trigger it. Once it triggers, it's going to stay in that state. It's going to stay in that state because my gate's been triggered. Well, what's going to trigger it? Our Darlington pair. Okay. And this is waiting for light in order to allow that to to form, excuse me, in order to put a voltage on the base of Q2 in order for this to work correctly. Okay. So again, basic principles, please don't get wrapped up around it. If you guys are having a quote unquote hard time with understanding this stuff, I don't expect you to be an expert, but you need to be able to recognize these. And I'm hoping that, at least at this particular moment, based off all the stuff that we've discussed, your own little research based off of discussion questions and a discussion post, you can see this and be like, yeah, that's an SCR. And that's what we want from you right now. Okay. To be able to recognize this stuff. All right, so I'm pretty certain that most of you are familiar with LEDs, light emitting diodes. We kind of took a quick peek at those. They may be in your house somewhere, from general lighting to your TV. Heck, even some of the monitors that you guys are watching me perform this on probably are LEDs. LED color varies with voltage. Okay, in electronics one, there's a voltage drop that's associated with the LEDs. Kind of quick plug here. If you're not really certain, please use those manufacturer specs or data sheets. But if you need a rough estimate or a rough guesstimate, 2.1 volts always seems to be safe, no matter the color. Okay, 2.1 volts is a safe voltage to use, no matter the color. Okay, if you don't know what it is, or if you're not certain. Okay, but some of the typical values that you're going to see are 1.7 volts for red. Okay, 1.7 volts for red. These are non-high brightness. Non-high brightness, if you can remember that. 1.9 volts is also for red, but these are your high bright efficiency. Okay, you have high bright efficiency, and then for this one, it's non-high brightness. Non-high brightness, high bright efficiency. For orange and yellows, it's going to be hovering around 2 volts. Okay, for orange and yellows. 2.1 volts. It's going to be hovering around for your greens. Okay. And then 3.4, 3.6 volts for your bright whites and most blues. Bright whites and most of your blues. That's the voltage we're going to be hovering around. Okay. So here you see the different elements that are created that are created in the substrate in the N junction. Okay, so this is just showing you the different elements. Once you're in forward bias mode, that means anode to cathode, as we've discussed quite a few times. This will heat up and it's going to allow current to flow. Thus, it's going to start emitting light. So before you had a diode, draw it out here for you. I'm going to draw it a little bit differently. That needed light to come in order for it to conduct. Okay, it's an opto isolate, optodiodes. An LED is the opposite. It's going to look very similar on the schematic, except notice which way the arrows are pointing. These arrows are pointing in the opposite direction because it's putting out light. Okay, it's putting out light. It's a little bit different. Okay, so these are different common LED packages. Nowadays, guys, they come in, gals, they come in all different shapes, all different sizes. Okay, so some of them may be maybe too small for you to even do anything with. I guarantee you the ones that are in your television or in your monitor are very, very tiny. They're tiny. They're almost well, they're not almost, they're manufactured chemically. And so you won't even see them busted down like this. But I suppose the best way you can see these honestly now, commercially or residentially, would be Christmas lights. Okay, or smaller little fairy lights. They have LEDs in them, and every once in a while, there will be certain types of medical devices that will have these types of LEDs in them as well. Okay. All right, so here we go again. We talked about this a little bit last week when we talked about IC chips. Okay. And you have two differing things that are happening here. And I'll jump into that in just a second. But basically, what you have is you have what's called a commercial optical coupler. Okay, optical coupler. And what it does is it transfers electrical signals between two isolated circuits. What are you talking about? Well, this is a circuit over here, and we don't know where these pins lead, but this is one circuit on this left side here. Okay. And on the opposite side, we don't know what's feeding or where this is going. We just know that it's coming into this particular circuit, but this is your second circuit over here on this side. And notice there is no wire in between them. Okay, so what you have going on here is you have an electrical signal being transferred between these two isolated circuits by way of light. Okay, you have an LED that's putting out light, and you have this transistor that requires light in order for it to conduct, and it's waiting on this LED to put that light out. Okay. So again, schematic symbol for an IC chip. You guys saw this a little bit last week. I pointed it out. Of course, we talked about how your pins would be located. They'd be going counterclockwise. We can pretend either there's the U up here, or maybe there's a little bit of a notch over here in that capacity, letting you know. Okay. So on pin 1, you have the anode of the optical LED. Pin 2, you have the cathode. Current would be flowing through the emitter with, and just kind of a quick uh, recovery or quick review. If you guys remember, 3 to 5% is going to be dropped on the base. I apologize. 3 to 5%. It's going to be felt on our base when it comes to the current. 95 to 97 is going to be felt on our, let's do this. Sorry, to 97 is going to be felt on the collector. And of course, on average, what you're going to see is roughly 100% felt on your emitter. Okay. Okay. So from the collector, of course, it's going to go when if current's flowing in this direction, it's going to go to wherever it's supposed to go on this chip. We talked about that a little bit. And of course, I talked a little bit about logic gates. Last week, I kind of went over an AND gate with you guys just a little bit, but this is the birthing, if you will, of a type of logic gate. Okay, and essentially what's happening is since there's nothing here that we can see, no resistors, nothing else, we can assume this is being used as a switch. So on pin 5, we're either going to have a high, a 1 coming out, or we're going to have a 0. Okay, we're not going to have anything come out. It's going to be a low. Every time this opto isolate, every time this LED over here flashes, it's going to be forcing this to conduct. Okay, so whatever triggers this to conduct will trigger this to conduct. That's how they're tied together. Okay. And of course, this kind of lets me put in my second plug. I want to say that next week, we're going to start diving right back into transistors. We're going to close out on transistors in week 6. I don't want you guys to feel like we're going backwards at all, but we kind of went this direction to explore these other differing components only because we knew we were going to come back to them because as you can see, they form the basis of a lot of our digital circuitry. Okay, so we're going to get back into them. Okay. So the components that we covered, guys, they barely kind of scratched the surface. Ah, man, there's so many different types of semiconductors. Thus, if you want to know more, please feel free to again research the resources that we've given you, review some of those videos, go online, take a look at them. There's a mountain of information out there. We don't dive into that deeply in this course, primarily because it's too much. We don't have enough time together. I can list a laundry list of these items, but we do want you to be familiar with them. Okay, we want you to know that they exist. We're going to kind of see some of these in action here in a little while. So with that, we're going to kind of dive into power supplies. Um, the purpose of a power supply, if you guys don't know, or if you're not familiar with it too much, is to turn an AC signal into a DC signal. Okay, and we're going to discuss 5 sections of the power supply. And I want you guys to remember this as much as you can. The first section we're going to talk about is we're going to talk about the input. Okay, so a power supply has an input. And the purpose of this, and usually it contains a transformer. Okay, so you're going to find a transformer inside of inside of here. Okay. And basically what it does is a transformer steps up or steps down the voltage and then sends the signal out to our next area, which is our rectifier. Okay, our rectifier. And the rectifier takes the signal. It's going to use some diodes. I'm going to show you pictures of this in action, so don't panic. I know I'm going kind of quickly with this, but I'm not trying to. Okay, and it's going to turn AC signal into a pulsating DC signal. So we're going to start out with something similar to this, and then depending on the type of rectifier, we're going to start to see this. Huh, okay. And you have a filter circuit. Okay, that's what the signal is going to go next. It's going to go to a filter circuit. Okay. Oh, yes, Jack.
Did you say the rectifier changes the AC signal to a pulsing DC signal? Was that
That
right?
is correct. Yeah, that
Okay,
is correct. Yeah, yeah,
thank you.
yeah. It is not clean, but it is definitely going to get there. So here you have, again, we're going to the filter circuit. And what we're doing is you're going to start to see differing things that take this now pulsating DC signal and they start to smooth it out. It's kind of like that. Jack, you raising your hand again, or is it stayed up? Oh,
Sorry, I
perfect.
stayed up.
No, no, you're good. You're good. Okay. So there you see now in the filter circuit, it starts to clean it up a little bit more. And then from our filter circuit, it's going to take it to our regulator. Okay. Not the Warren G. type of regulators, but they're just a regulator. I'm going to put that in reg there because I know it's an R. Okay, it's regulator. And what this is a voltage divider network or a Zener diode. We talked about that a little bit. It's going to regulate to maintain a constant DC voltage. Okay, so now what we're going to start to see is this DC voltage maintained constantly, constant voltage. And the last thing that this is going to be kind of involved with this, it's not necessarily going to be connected to it. I'm just going to kind of draw some dotted lines here, but it's going to be your protection circuit. Okay, and basically what it is it protects our circuits from overloading. So this is going to include fuses. Okay, we have fuses. Maybe we'll have circuit breakers. All right. So something along those lines. Not every circuit's going to have fuses and circuit breakers, but it's going to have something to protect it. And that P looks terrible, so let me fix that. Sorry, there we go. Looks even worse than it did before, but you guys get the idea. Okay. All right. So jumping back into transformers, essentially what transformers are is they look like two inductors or coils that are facing each other. Okay, you have a primary and a secondary, and the primary always has your input signal. Okay, the primary always has the input signal. So if it looks something like this, here we go. Okay, this would be our primary. And then I'm going to purposely draw only 4 windings on our secondary. Okay. All right. More windings on the primary, as you can see here, versus the secondary will indicate a step-down transformer. Okay. This is stepping down. If I wanted to step up, it would look something like this. It would look just the opposite. You would have your primary with fewer windings than your secondary, showing you that we're stepping it up. Okay. The double dots basically mean that the signal is going to be going straight across. So if you see signals looking like this, double dots, oops, sorry about that, means our signal is going to be going straight across. Every time I draw a dot, it doesn't want it there. All right. So essentially what you'd have is you'd have this AC signal coming in. And because it's going to be, when we say it's straight across, it's the exact same thing. It's just a little tinier because it's been stepped down. Okay. All right. And the opposite would be true over here. Okay. If you don't see 2 dots, guys, assume that the polarity is the same. But if you see the dot over here on this side, and then you see the dot over here on this side, what this is telling you is that the polarity is opposite. Okay. That's what the polarity is telling you. Okay. That's opposite. Okay. So again, pretty much when it comes to that, well, let me rephrase it or let me add something else here. Your primary voltage ratings that we're going to be looking at are going to be 110 to 120 volts. So 110 to 120 or 110 to 240. Okay. These are the different voltages that we're going to be seeing. Yes, Daniel.
Hey, so if the voltage is being stepped up, what's being sacrificed in order to compensate for that?
Usually you'll see it in current.
Current, okay,
Yeah,
gotcha.
yeah. You'll see it in current. And so we don't dive too much into uh that particular instance. I don't recall if it's in the reading or discussion question. I can't remember off the top of my head. One of the reasons why we saved you guys from that during the lecture. But that is some of the stuff that you see being encountered when it comes to that. Just really quickly, when it comes to the beginnings of power supplies, I want you guys to think of your laptops, okay? Or yeah, most of you guys, if you don't have a laptop, what you'll see is you'll see the AC end of it that'll plug into your wall, and you're essentially plugging it into. Technically, it's 115 Reality, though, it's somewhere between 110 to 120 volts is being put out. And what that's doing is it's taking that 115 volts and maybe to your laptop, the little DC plug at the very, very end of it, maybe it's shaped like an elbow when it comes off the cord that's connected to everything. Maybe it's 15 volts VDC. Okay. So if you can imagine everything that I'm about to describe to you is what's happening inside of that power cord, okay, inside of that power supply or the power charger, if you will. Okay, so again, here you see your transformers, and this is what you're going to mostly find inside of your inputs. Okay. All right. So a couple of things going on with this. As I'm describing the circuit in front of you, we are going to take a look at this in action because I wanted you guys to see the rectifier, if you will. What's happening is that's the next part that we're at. But while I'm doing that, go ahead and take a look at that interactive question. The question is pretty simple. It says what do and do post it in the responses in your chat in the chat. It says, what do the two solid lines shown in the transformer indicate? I didn't talk about that intentionally. So if you know it off the top of your head, educate the class. If you don't, do a little quick digging. That is correct. Daniel got it right off the bat. It means iron core. Okay, those are those two solid lines there indicate there. Okay. All right, so what we have here is a half wave rectifier. All right. And something I wanted to show you is I'm going to draw a dotted line to help visualize this. Again, on the left-hand side here, what we have is we have our power supply, okay? We have our input. Sorry, let me back up a little bit. This is our input on this side. And we just covered this area. And on over here is our actual rectifier. Okay, and that rectifier, we're going to spend a few slides going over rectifiers. There's quite a few of them, but basically what you see in front of you is a basic half wave rectifier. Okay, so half wave, the easiest way to tell is it's got one diode, and that diode is located right there. Okay, so the diode is either going to be on or it's going to be off. Essentially, it's just going to pass half of the wave. Okay, so we'll pretend that what comes out of this on this side is a nice, beautiful sine wave. On this side, though, in conjunction with the load resistor, depending on which way this AC signal is polarized and which way this diode sits, you're going to start to see pulses coming out. And I'm going to show that to you guys in a minute, how it all looks together. Okay. So let me get over there and pull this up. Something I wanted to note to you guys as well. I think I talked about this a little bit last week. Okay. There's over 2 million circuits that are kind of built into this simulator. We haven't built them ourselves, and so the visualizations aren't going to specifically match what's in the reading or on the powers or on the PowerPoints, and that's okay because really what I want to do is I want to give you the visual. Okay, and you can clearly see we've got a nice AC signal or DC signal kind of pulsating here coming out on top. And it's because of what's going on in this circuit here. So just know, please don't get hung up on them not matching. Again, the idea is to kind of present this image to you guys. So if you can imagine over here, instead of this AC signal, imagine if you could that this is the secondary part of the winding for your from the transformer. Okay, and coming off of it is this AC signal. As it hits this diode, okay, the diode only conducts whether it's in forward bias versus reverse bias. So every time the polarity isn't in reverse bias, the diode will not conduct. Once it goes into forward bias, it conducts. And what you have happening in conjunction with the load being dropped on this 100 ohm resistor on this right-hand side here is you start to see these pulsating waves coming out. Okay, that's how it's created. All right. And there you see on the top what you would visually see. So this is the half wave rectification that's occurring. Okay. So again, as I kind of demonstrated a little bit to you guys, if I were to, and I talked about this just a second ago, if I were to flip this the opposite way, what you would see on our simulator is instead of seeing this beautiful pulse wave going up and down like this, you would start to see these pulses instead. Okay, so it's just going to depend on what it is the engineer and what it is the circuit needs for rectification and which way the polarity of the diode faces. And this principle is true of every one of the rectifiers I'm going to show you guys. Okay, so we're not going to spend a lot of time on every one of the configurations, nor do I want you to think that all the time it's a positive pulse. It's not. It depends on how the circuit itself gets set up. Okay. All right. So one of the things I think you kind of notice with this though, is that while half wave rectification does work, it's not the most efficient signal output. We're losing a lot of signal. Okay, so ideally what we want is we want to get that entire signal to get what's called full wave rectification. Essentially, we want a nice ripple. We want to go from something that looks like this, maybe to something that's looking like this, getting closer to that steady DC output. Okay, and a circuit that gets us closer is what's known as a full wave rectifier. All right. So this is a full wave rectifier. Okay. It's got two diodes. And essentially what's going to happen is when one of the diodes is on, based off of the principles that I just described to you, the second one is going to be off. And they're going to, when the polarity shift, it's going to flip. Okay. The diode that was now off will be on, and the one that was on will now be off. Thus, it's going to be passing the entire waveform. Okay. So what this looks like as it passes the entire waveform is something as follows. We get full wave rectification. Okay, so again, here's a full wave rectifier. Configuration is looking a little bit different. Something I didn't point out to you guys and talk about before, but since I have it up, I can. Here's a really good indicator of an iron core transformer. Don't get wrapped up on the way the windings are showing. Sometimes they're displayed that way, but notice it says 12 to 1. This is showing you that it's a step down transformer at a 12 to 1 winding rate. Okay, and this is center tapped. Anything that's center tapped is showing you essentially you'll have this little, the ground will be right in the middle, which means you can get two different, you can take and tap off of two different phases. And so what's happening here is these minuscule little pulses that are really, really tiny. Every time one of these bad boys conducts in this current configuration. So when this one is conducting, this one is off. And when this one is conducting, this one is off. And they flip back and forth between the two of them. What you get on your output, as felt on this load right here, is this nice, beautiful ripple. Okay, this is what full wave rectification does for you. Changes the wave from half wave to full. Pretty straightforward and pretty simple. All right. And finally, we have what's called a bridge rectifier. Okay, this is still a full wave rectifier, but as you can see, it uses diodes instead of resistors like a Wheatstone bridge did. If I'm asking you guys to go back to Electronics 1, you may remember the Wheatstone bridge had 4 different resistors in a certain configuration. So this is very similar to that, except you have your 4 diodes. Okay. D1 and D4 are parallel to each other, and D3 and D2 are parallel to each other. And of course, the easiest way to tell they're parallel is the direction they're facing. They're facing the same direction. Okay. In order for this to all work, this has to be configured this way. So no matter which way you see it, as long as these pairs are facing the same direction, this configuration will work. Okay. And as I touched on earlier, if I flip the diodes, all of them in opposite directions, it's still going to work, but we're going to have a negative pulses instead of our positive ones. Okay, well, negative in reference to what they could be. Okay. One of the problems that you're going to run into when it comes to utilizing this many diodes is heat generation and dissipation. Okay, so quite a few times engineers have tried to have had to battle heat dissipation and generation as best they could. So it's not uncommon to see these types of bad boys get really warm and need some type of cooling, if that makes any sense. So let's get into our full wave, our bridge rectifier. I apologize. All right. Here is our bridge rectifier. Okay. And so essentially you have your diodes. Again, it's a slightly different configuration, but talking through this here, you see your 5 to 1 iron core step down, non-center tapped. Okay. The way this is facing is you have these two diodes are parallel and these two diodes are parallel. That's why this configuration works. And then off here on the right, it could either be an open end because it leads to something else, a load of some type. But essentially where you see is this 1K resistor that's kind of sitting here. And what we're looking for is this is showing you actually two different signals. The first is the green one here that you see, which is this long AC sine wave. And then here you see your DC output. Look how nice and clean and not so ripply it is. All right. Very, very clean. Still not perfect. And with further rectification, you can get it there. You can smooth this out even more. Okay. Till we start going into the filters, which we're going to discuss here in a little bit. But this, ladies and gentlemen, is what a bridge rectifier looks like and how it operates. Okay. All right. And so here, what we're going to start getting into is our filter circuit. So this is the third phase, the third step. Okay. So we go input, we go rectifier, and now we're in filter. Okay. Filter circuits have a capacitor and a resistor, or they have an inductor and a resistor. All right. And we're going to focus right now currently on the capacitor and the resistor. Okay. So this is a half wave rectifier with a capacitor filter. The primary goal of the filter circuit is to clean up the output of the rectifier, or rather start to clean up the signal. So we want to get rid of that ripple. We want to start smoothing it out as best we can. Okay. Something to remember, and we've touched on this a bit throughout the course, and I know you guys did a lot in Electronics 1, is that a capacitor will store charge until it has a path to discharge. So when it starts to discharge, you're going to start to get this sawtooth effect. Okay. You have this sawtooth effect occurring because you have half wave rectification. If you can start to lean forward with this and imagine, well, what would it look like if I had full wave rectification? What would this start to look like then? Okay, so just kind of keep that in the back of your mind as we look at this really quickly. And we're going to take a look at our. All right, allow me to zoom in so you can see the circuit a little better. Okay. So again, here we have the um, half wave rectification with capacitor. Okay, so you can see the capacitor down here on the bottom. It's charging up and then it's slowly discharging, and then it's charging up again every time this diode conducts based off of the input signal that's coming into it. So this is what the AC signal would normally look like. Here you can see though that when you start to add this filtering using this capacitor along with this resistor, you start to slow down the discharge and you start to slow down that waveform. Okay, so we're going to start to see this get even more shorter and more impressive as we start moving into some other types of filter capacitors. Okay. Okay, so again, this is just kind of a quick review. You see the input signal. I just showed you guys what that looked like. Here you see the output signal without a capacitor filter. And of course, here you see the output with a capacitor filter, as we've just demonstrated, as we've just kind of looked at. Okay, so these are your differing effects of differing filter capacitors. Okay, so again, unfiltered output, you guys get the idea with that. Here you see the output with the small filter capacitor and the larger filter capacitor, that fall time isn't so steep. So it's a little bit smoother. Okay. Just keep in mind that regardless of the cap size, it still isn't going to be the best. It still isn't the best signal. Okay. So if you can imagine at full wave rectifications where we have this nice steady ripple, in between, if I start to discharge, I'm already charging again. See that? So now what you end up with is this nice, cleaner DC signal. It's got some rippling to it, but you have a nicer DC signal. Usually what you'll see when it comes to this is first it'll get filtered, then it'll get filtered again, or it might get rectified 2 or 3 times and it gets filtered twice. So we get rid of that little rippling effect and we get a nice steady signal coming out there. All right. But that's the principle for the first 3 areas. And we'll start getting into our voltage regulators. Okay, so what we have coming in here is some type of input rectified filtered signal. Okay, so you're no longer dealing with ACs. You're no longer dealing with these half waves or even these. What you're dealing with now is something that looks kind of like this, okay? It's a little bit of an exaggeration, but it's pretty close to a straight DC signal. Maybe this is 5 volts. Let's see if I can find it again. And this is 6 volts, and this is 4 volts, and we're hovering somewhere in between that 1 volt range. It's pretty sarcastic and a little bit large and exaggerated, but you get the idea. Okay, it's pretty tight there. All right, so the Zener diode is going to be operating off of a breakdown voltage. All right, we talked about this before. So the breakdown voltage for this particular Zener diode, if I wanted to give you one, and just remember that breakdown voltage is also known as VZ. We're going to say that it's set to 16 VDC. Okay, 16 volts. So essentially what's going to happen is it's going to hold and clamp at 16 volts. That's what it's going to hold at. So for whatever reason, this spikes up to 24 volts. Well, it's really messy. 24 volts. If this is at 16, it's going to hold at 16. It's going to clamp to that 16. Okay. So whatever we see, the filtered output signal as it comes out, that's what it's going to be regulated at. So these 2 test points right here, we would see 16 VDC going to wherever else in the circuit that you wanted it to go to. Okay, the whole point of the regulator is to maintain or regulate the voltage. A voltage divider network can be utilized, which would contain resistors or even transistors that set up the network to maintain the set voltage. This is just showing you one resistor. Again, the whole purpose of the voltage divider network or the voltage regulator network centered around a Zener diode, okay, centered around this is to maintain a set voltage. Okay. This is a shunt regulator, okay, using a transistor. So I just told you before that when it comes to regulating circuits, the mainstay in most of them is a Zener diode. Why? Because it's clamping to a certain voltage. However, you can have a voltage divider network, that's what this is, or a regulator, sorry, a regulator voltage regulator network that's made up of diodes, it's made up of transistors, it's made up of resistors. And this shunt regulator is made up using this transistor. Okay, so the Zener diode itself is going to set the base bias. You remember again, this is our base. Here we have our collector, and here we have our emitter. And for those of you that remember this, this is not pointing in. So what type is it? It's an NPN. Okay, this is an NPN type transistor. And your output is going to be whatever is coming across the collector of Q1. Okay, so whatever is coming across this collector is going to be your output here. You get unregulated DC that comes in, essentially. That's what this is. So that unregulated filtered DC signal is coming this way. And then out here, you get a regulated DC voltage out. That's the purpose of this particular voltage regulating network. Okay. All right, so here we have a voltage regulator. RL represents a load resistor. Okay, so when you see RL, this is just in here to show you that this could be a light. Okay, this could be a winding to a motor. This could be some type of winding to a contactor, or maybe a relay, right? It could be multiple things that would get energized. Okay, would get energized in some capacity. So load equals all these different things, anything that's going to be dropping the voltage. Okay. You also have a variable resistor. We talked about this a little bit a couple of weeks back, or last week was it? We talked about variable anything, and it's indicated by this little arrow that's kind of pointing right to it. Okay, so basically this is telling us that we could increase or decrease the resistance, almost like a thermostat. Maybe we want to increase or decrease our temperature. Okay, so essentially this is the regulated voltage that's going to be going to our load, is what this is depicting a little bit. Okay, so here is a series regulator. Okay, the Zener diode is going to drop 0.7 volts to regulate on the base of Q1. So here's that Zener diode again. Guys, I think by now, if you should kind of have caught on that anytime you see the Zener diode, this is the third time I've said it, in a power supply circuit, it basically means that it's talking about this being your regulating. All right, this is your regulating portion of your power supply circuit. Okay, the output will be coming across the collector of Q1. Okay. There's the output. It's going to be coming across the collector of Q1, which is right over here. Apologize. Oh, no, over here. Sorry. Oh, this is the emitter. This is our collector. This is our base. Okay. Volt out or E out is your VZ. So this is known as the base to emitter voltage. Okay, so base to emitter voltage is volts out or the VZ. Okay, we talked about that a little bit previously. It's things all over the place. I apologize. Okay. And then so whatever voltage drop is across is basically going to be your only voltage loss. So whatever the voltage drop would be across here is really all you're going to be losing when it comes to that voltage drop. Okay, and of course, again, as before with the other items, the regulated DC voltage is what's coming out. As I press forward here, I do want to showcase the second and final interactive question that we have for the evening. It says, which type of regulator, series, or shunt is considered more efficient and why? So go ahead and drop that response in the chat as we walk through this. Okay, I'll give you a couple more seconds to read that question and toss it in there. Okay. Voltage multipliers are for when you are trying to get a higher DC voltage. Okay, this can be demonstrated by simply connecting batteries together. Okay. As you place them in series together, you're increasing your voltage. When you put them in parallel side by side, you actually will increase your current. Okay, so here you see voltage multipliers, as I just stated, that provide a higher DC voltage than the input without the aid of a transformer. So if you start hearing about voltage multipliers, this is what they're doing. You also have voltage doublers and you have voltage triplers. And again, they work on the same principle by providing either double a DC voltage than the input, or they triple that DC voltage without the aid of a transformer. Okay. Okay, so last thing after we get out of our regulator is our protection circuits. Okay, so here you see a crowbar or an overprotection circuit. That's what this is called, crowbar overprotection circuit. Say that one more time. It's a crowbar overprotection circuit. We have our voltage divider network and R1, which is our gate trigger. Okay, so this part right here is your voltage divider network or your regulated. Okay, this is our regulated portion of it, our regulator. Sorry. And then on this side over here, everything to the right of this over here is your protection. Okay, the final area that we talked about. Okay. Whatever voltage is coming across is going to set our trigger. Okay, whatever voltage comes across will be setting our trigger. Once the trigger sets, current's going to flow. Okay, once current flows through the SCR, this will be the path of least resistance. So recall that this is a protection device. If you want to take voltage away from here, we want it to flow through the path of least resistance, right? We don't want it to flow through something that we don't want it to flow through our load, okay, at all. We want it to flow through somewhere else. Thus, the SCR gets turned on, and that allows us to take that away from there. And of course, the SCR, as you guys recall from last week, is going to remain on until it gets put into a reverse bias state, or the anode voltage will be taken away. So, kind of building upon this principle of SCRs, I mentioned it last week. They're used as a form of protection in protection devices and for circuitry. Okay, protection components. This is how, and this is where, primarily within a power supply in this circuit over here. All right, here's some fuses. Fuses come, guys, in all shapes and sizes, if you don't already know that. Fuses are cheap. Just throw this out there to you. I'd rather have a fuse blown than blowing a piece of equipment or damaging a patient. Okay, so this type of protection is pretty good. They are overprotection. They're primarily there for amperage protection, so you never want to go over the amperage. Okay, so make sure you're in those data sheets, you're familiar with the manufacturer's specifications. They operate on the principle of causing an open to kill a signal for a circuit. Okay, so essentially on a schematic, what you might see for the fuse is you might see the signal look something like this. Okay, it looks just like that. And this, of course, the signal comes. Well, as you guys know, if I break it or I open it, current can't flow, right? It's exactly how this works. And so the idea here is that at a certain amperage, this filament gets too hot. And once it gets to a certain rated heat, it will open up. It melts it. Okay, so it's designed to protect the circuit by that way, by simply shutting, by not allowing current to flow. Okay. These are rated. Again, I said before, you never want to go over the rating when replacing them, as you want them to fail. Okay, that's their purpose. You do want them to fail. When they blow open, if you will, the gap in the wires, it causes an open, kind of as I just demonstrated there. So if you were to try to measure resistance across this, let's say you took this out and you put your settings under multimeter to resistance, or even to the, what I like to do is the diode checker on it, because the diode checker has a little symbol, looks kind of something like this. It's got the diode and then it's got this little buzzing sound. Okay. And if it's a straight piece of wire through here when you're measuring, you get a tone. So if you were to do it with a perfectly working fuse that's designed to only be a piece of wire, that's all it is, you'll get you'll start to see something that's less than um, an ohm of resistance, because there's basically, it's a straight piece of wire and you hear a little tone. Okay. If you do it over here on this one, what you're going to see oftentimes is this overload. It's max resistance. That's what that means when you see OL. And it's the max resistance because it's open. Okay. So you want to make sure you understand that and that you're familiar with that a little bit. Okay. All right. Circuit breakers, they are used for protection as well. I think you guys may or may not be pretty familiar with those. Sometimes they can be used as switches. They trip when oversurges occur. They usually have a specific order to reset them. Okay, so sometimes when you reset them, you can't just reset it. So let's pretend that your circuit breaker, we're looking at it from the top view or from the side view. We'll pretend that it's in this configuration, okay? And up means on, and then down over here, if it was down over here, it would be off, okay? Well, oftentimes when they trip, what they do is they pop to the middle. Okay, so it's sitting right here. It will not let you just turn it on. You can't just turn on a circuit breaker sometimes. You have to reset it. In order to reset it, you have to flip it off from its trip position, and then you can flip it back on. Okay, so keep that in mind if you ever encountered those as a certain type of circuit protection. All right, ladies and gentlemen, that concludes week 4. Thank you for joining me this evening. Next week in week 5, we're going to jump back into transistors. We're going to talk about them as amplifiers, and of course the differing classes of transistors and how they work. And for the last week, week 6, we're going to go over transistors some more. We're going to talk about them as oscillators, and how they take and turn random signals into set frequencies, such as sinusoidal AC signals. So we're going to get into that a little bit. As you guys have done, if you have any questions, please ask me, let me know. I check emails relatively often. If you respond to me and I don't respond immediately, it's not because I'm ignoring you guys. I get in there every day, if not every other day, to see what's going on, look at grades, but I'll do my best to reply as best I can. So with that, you guys have an excellent rest of your day, excellent rest of your week, and let me know if you guys need anything.
Thank you. You too.
Thanks, Chris.
Welcome.
Thank you.